Okay, so hello. We're going to be talking about gas laws today in class. We have two types of laws that we're going to be talking about, and then we're also going to be talking about the combination of the two. So the first one is Boyle's law. Boyle's law is a relationship between the pressure and the volume. It says that the pressure times the volume is equal to a constant. So another way that we can write it in the equation that we're going to use to solve is we're going to say that the pressure times the volume at point 1 has to equal the pressure times the volume at point 2. So when we talk about point 1 and point 2, we're talking about time. So I'm going to take the pressure, measure the volume of a situation, and then sometime later, the pressure and the volume have to be equal to the initial pressure times the volume. The second law that we're going to be talking about is Charles' law, and this is the relationship between volume and temperature. This is saying that volume over temperature is a constant. So that means the volume 1 over temperature 1 equals volume 2 over temperature 2. What happens here is that if, back to Boyle's law, if pressure goes up, volume goes down. In this case, if volume goes up, temperature goes up as well. So we're going to be talking about those two relationships. Okay, so now the ideal gas law is the combination of Charles' law and Boyle's law. So we have two things. We have PV, the pressure times the volume, equals nRT. And T is the temperature. And we're going to talk about what N and R equal to in just a second. If we put those two equations together, we have Boyle's law on the top, P1 V1 equals P2 V2, and then the P and the T over here, and the V and the T over here is Charles' law. So we have P1 V1 over T1 has to equal P2 V2 over T2. And so we're going to have these relationships where we can find any of these information. We can also compare it between two times in two lab experiments. Okay, so let's look at this a little bit closer. The P is just the pressure. Excuse me. When we have a relationship where we're saying this equals this, the values, the SI units for pressure don't matter because you would be dividing through, and so you don't have to do any conversion. But when you're using this equation, you have to make sure that pressure is measured in pascals. The V is the volume, and that volume has to be measured in meters cubed. The N over here is the number of moles that you have. So that's back to chemistry, so we're going to do a little bit of chemistry in here to find out the number of moles. And I'm going to skip the R for a second, but T is our temperature, and that has to be measured in Kelvin. So we're going to have to be doing some conversion to Kelvin. Now let's look at the R. Well, the R is a constant. It's called Boltzmann's constant, but R is always equal to 8.31 Pascal meter cubed per mole degree Kelvin. And you can look at the units here, and that's why pressure has to be in pascals, volume has to be in meters cubed, N is the number of moles, and it has to be in moles, and temperature has to be in Kelvin. So we're going to try some examples using the ideal gas law. Most of you should have known this and learned this in chemistry. Okay, so let's try an example. Okay, we have a house whose volume equals to 80 meters cubed. So here is our given. Our volume is 80 meters cubed. Contains air at a pressure of 1 atmosphere. And at a temperature of 20 degrees Celsius. How many molecules of air are there in this home? So our unknown is N, the number of molecules. Okay, so the first thing is our volume's in the correct units, but our atmosphere is not. So we have to convert the 1 atmosphere to Pascal. Well, 1 atmosphere equals 1.01 times 10 to the 5th Pascal. So if we finish this off, we have 1.01 times 10 to the 5th Pascal. So that is now our pressure. Now our temperature has to be converted to Kelvin, and we know that all we have to do is add 273 degrees. So we end up 293 Kelvin. Okay, knowing all this, we can go into our equation. We know that PV equals nRT. We know the pressure is 1.01 times 10 to the 5th Pascal. Our volume is already in the correct units. It's 80 meters cubed. We're going to divide by RT. R is just a constant, 8.31. And it's Pascal, meters cubed, mole, Kelvin, times T, which is 293 Kelvin. So if we multiply this out, we end up with, and I don't have the answer here, so anyway, you can multiply this out and find out the number of moles that are in the air inside of a home of this size. Okay, let's try one more question. Okay, the air pressure of a car tire is 207 kilopascal, and its temperature is 27 degrees Celsius. As the car is driven along a highway, the temperature of the air in the tire increases to 57 degrees Celsius, and the volume increases by 5%. What is the final pressure of the tire? So we know our initial pressure is 207 kilopascal. The initial temperature is 27 degrees Celsius. The initial volume is just going to be V. We don't know what it is, we just know that it's volume. We also know that the final temperature is 57 degrees. The second volume, it says, increases by 5%. So it's going to be the initial volume plus an increase of 5%. If we add this is 1V plus 0.05V. We have 1.05V. What is the final pressure? We're looking for P2. So what we're going to do here is we're going to use the equation P1 V1 over T1 equals P2 V2 over T2. So we have two situations here. We say the temperature of the air increases. So as the car is driven later on, what happens? Well, we know P1 is 207 kilopascal. We know volume 1 is just V. And T1 is 227 degrees, but remember it has to be in Kelvin. So we're going to add that, and we have Kelvin. And now P2 is our unknown. Well, V2 is 1.05 V, and T2 is 57 degrees plus 273 Kelvin. So if we do a little bit of calculation, and look here, these V's will cancel out, and so we can solve for P2, and P2 ends up being 216.8 kilopascal. So we can find out what the pressure is later on as the volume increases and the temperature increases as well. So this allows us to look at two situations, a before and an after, and compare the values. Okay, we're also going to talk about, and I don't have a slide here, but thermal expansion. And thermal expansion is going to be how, as temperature rises or falls, things will increase their length or their area. So for instance, if you look at a sidewalk, most of the sidewalks that we have have little slits in between. So if you have a sidewalk, you're walking down, there's a little space in between. Well, the reason why there's a space in between there is because during change in temperature, these sidewalk, the concrete, will expand and contract based on the temperature change. And so this allows for it to expand and contract. So as the temperature goes up, these sidewalks will increase their size, and this gives it space to do that. Otherwise, what's going to happen is these two sidewalks, when they expand, will end up cracking, and you're going to see a lot of that. You also can know, if you go over a bridge, sometimes you hear that thunk, thunk, thunk sound. Well, what happens on a bridge is they put these little metal expanders in between the bridge. And what happens, once again, that allows for the bridge not to crack when the temperature changes. Another example of thermal expansion is if you put a can of Coke in the freezer, what happens? The temperature decreases, and you're going to have that can explode. So we're going to talk a little bit about that. As the temperature goes up, the volume or the area of a property will go up, and as the temperature goes down, the volume or the area will go down as well. There's no formulas that we're going to be learning at this level, but I just want you to be aware that things do change their size as well as the temperature and the pressure and the volume, and that's based on thermal expansion. So we'll see you tomorrow. Don't forget to do the assignment, and we'll be doing some classwork tomorrow. Bye. Have a good night.